You may remember that reaction from the foundation course, when the reactions between alkali metals and water were demonstrated, and how violent some of them were. If sodium metal is added to water, a vigorous reaction takes place. On reaction, sodium hydroxide is formed and hydrogen gas evolved. Here's another reaction. Ethene gas from a cylinder is passed into chlorine gas. In time, after about 2 hours, the green color of the chlorine gas fades as ethene reacts with chlorine to produce a colorless liquid 1,2-dichloroethane. Here's a reaction you'll meet later in the course. If lithium aluminium hydride is added to ethyl ethanoate, a vigorous reaction takes place, giving off sufficient heat to ignite the ethyl ethanoate and the product of the reaction, ethanol. A reaction you will meet in Unit 10 is this one. If 2-naphthol is added to benzene diazonium chloride at a temperature below 5 degrees centigrade, then a bright red dye is formed. Obviously, all of those reactions go. But why? Why does this reaction of sodium with water to produce sodium hydroxide and hydrogen go? Why do they go in this direction rather than in the reverse direction? Sodium hydroxide and hydrogen do not appear to react to form sodium and water. So why is this? Why do reactions have this preferred direction? Let's consider some familiar processes which occur of their own accord. Processes we call spontaneous processes. Waterfalls fall. Like the chemical reactions we've seen, there is a preferred direction because the water flows from a higher to a lower level, reducing its gravitational potential energy. Apples also fall. Lightning is the flow of electric charge from one potential to a lower potential energy. Similarly, springs spring. The spring in Jack is tending to reduce its strain energy. And magnets, if I bring this magnet closer to this one, a spontaneous process occurs and the magnets seek a reduction in magnetic energy. All these processes are spontaneous. They all occur of their own accord. In each case, there's a reduction in a particular kind of energy. Is this true for chemical changes, chemical reactions such as sodium with water? For every reaction that takes place, there is a reduction in a particular kind of energy of the system. This is the Gibbs energy, and it's usually plotted as G system versus a quantity called the extent of reaction, and it reveals the spontaneity or otherwise of chemical processes. If the Gibbs energy of the system can decrease, then the reaction will be a spontaneous reaction. If, on the other hand, the Gibbs energy of the system increases, then the reaction can't take place. Let's consider the reaction between ethene and chlorine again. The reaction is ethene in the gas phase reacting with chlorine in the gas phase to form 1,2-dichloroethane in the gas phase, which eventually condenses as a liquid. Let's see if we can plot the Gibbs energy of the system versus the extent of reaction. Gibbs energy values for particular substances can be determined experimentally and are listed in tables like this, usually under conditions of 1 atmosphere external pressure and at 25 degrees centigrade. When the values are listed at 1 atmosphere pressure, the values are given the symbol G0. However, we can't determine absolute values of Gibbs energies, just as we can't determine absolute values of potential energy, because we don't know where the 0 point is. but we can select an arbitrary point of 0 Gibbs energy and then quote all values relative to this point. Because of this, Gibbs energies referred to this arbitrary 0 are usually labelled delta G naught F. But for simplicity, we shall refer to these as G naught values. It doesn't affect the argument. So let's look up the G naught values for each of the reactants at 25 degrees C. G naught ethene gas is plus 68.1 kilojoules per mole, and G naught chlorine gas is 0. So the total Gibbs energy of the system before any reaction takes place, that is when the extent of reaction is 0, is 68.1 kilojoules per mole. We now have one point on our graph of G system versus the extent of reaction. We can also put another point on the graph. When only products are present, that is when the reaction has gone to completion, and the extent of reaction is 1.0, G system is equal to G products, which is equal to G naught for 1,2-dichloroethane in the gas phase. From the data book, this value is minus 73.8 kilojoules per mole. So now we have 2 points on our graph. But how are these 2 points connected? Can the points be joined in this way? Well, obviously not. We know that if a reaction occurs, the Gibbs energy of the system must decrease. With this curve, if we started with pure reactants, they would stay as pure reactants when mixed. If we started with pure products, then the system would remain as pure products. Well, how about a straight line joining the 2 points? Does this seem feasible? Well, yes, it does. The Gibbs energy of the system can decrease by a reaction taking place. So reactants will be converted into products. Reaction will continue until the Gibbs energy can decrease no further. This is at extent of reaction equals 1 mole. That is, at pure products. Well, it looks right, doesn't it? But hang on a minute. If only products are present at the end of the reaction, what is the value of the equilibrium constant for this reaction? If the concentration of chlorine and ethene drop to 0, then the value of the equilibrium constant would be infinity. Although the equilibrium constant for this reaction is large, it is not infinity. No reaction can produce pure products. So what does this mean for our plot of G versus the extent of reaction? Well, it looks like this. A curve with a minimum value of G close to, but not at, the position of pure products. In fact, we've exaggerated the curve here. The position of the minimum for this particular reaction occurs when the extent of reaction is 0.999. So, if we start with pure reactants, the reaction will take place until the G value has reached its lowest possible value at this point here. Once here, no more products can be formed, and no more reactants can be formed by a reverse reaction. This is the point of chemical equilibrium. In fact, chemical equilibrium is defined as the position at which the Gibbs energy of the system is a minimum. So this is it. What about the reverse reaction? Well, the curve tells us that we can never get pure 1,2-dichloroethane. Dichloroethane will spontaneously dissociate into ethene and chlorine until the minimum point on the curve is reached, at this point here. For the reaction between ethene and chlorine, the difference between the G values for pure reactants and pure products is quite large, and the position of the minimum G is way over towards the product side of the equation. For the reactions in which the difference between the Gibbs energy values for pure reactants and pure products is not as great, so the position of the minimum moves. When we consider reactions in which the energy of the reactants equals that of the products, here, then the curve can become symmetrical. Reaction can still take place, but the position of the minimum is midway between reactants and products, and the value of the equilibrium constant is 1.0. As the Gibbs energy of the products relative to the reactants increases further, so the minimum moves, and moves towards the reactant side of the equation. Well, let's summarize the arguments so far. Reactions take place to reduce the Gibbs energy of the system. When G has reached a minimum value, no more reaction can take place. This is the position of chemical equilibrium. And the value of the equilibrium constant is related to the difference in G0 values between pure reactants and pure products. Let's now apply these ideas to some other chemical reactions. These are some of the chemicals you've received in your home experiment kit. Here's benzoic acid, which you used in home experiment 1. And here's a sample of toluene, which you used in home experiment 2. Here's one of the chemicals we've sent you in the kit, ethanol. In fact, it's a very pure sample of ethanol. But let's consider this reaction involving ethanol. Here, the G0 value for the reactant ethanol is minus 174.1 kilojoules per mole. G0 for the products is minus 50.8 for methane, plus minus 237.2 for water, and 0 for carbon. A total of minus 288 kilojoules per mole. A plot of G's system versus the extent of reaction will therefore look like this. The minimum value of G here will be very close to the product side, the right-hand side of the equation. So this reaction should be a spontaneous reaction. Ethanol should spontaneously decompose into methane, water, and graphite. But this bottle of ethanol was purchased some months ago, and there are no signs of graphite being deposited or methane gas being evolved. So what's gone wrong with our argument?
Well, you may remember that the Science Foundation course developed the idea that there are two criteria to be considered when predicting whether or not a chemical reaction will go. We've been considering the Gibbs energy criterion, the so-called thermodynamic approach. And certainly ethanol should decompose according to thermodynamic arguments. But we must also consider kinetic factors, how fast a particular reaction proceeds. The Gibbs energy values can tell us whether or not a particular reaction is thermodynamically possible, but it gives us no information on the rate of that reaction. So, if a reaction is thermodynamically possible, yet very slow, we won't see the reaction occurring. Now that's just what's happened in our ethanol decomposition. The reaction is thermodynamically probable, but the rate of this reaction must be very slow indeed. So let's consider some of the factors which influence the rate of chemical reactions. The rate is related to the activation energy for the reaction, the energy barrier to the reaction. You'll no doubt remember energy plots like this. This shows how the energy of a reacting molecule changes as it's converted to products. There's a hump or barrier which it must surmount.
But I've just developed the argument that for a reaction to proceed, the Gibbs energy must decrease.
And what I'm saying is that the energy goes through a maximum on passing from pure reactants to pure products. Both plots are correct. In order for the reaction to proceed, the Gibbs energy of the system must decrease, but the energy of individual reacting molecules goes through a maximum.
I'm considering the Gibbs energy of the whole system of molecules, a very large number of molecules.
Whereas I'm considering the energy of many individual molecules as they react.
But the sum of all these plots brings us back to this plot.
Any molecule trying to react meets the energy barrier. And each molecule with sufficient energy to surmount this barrier can go on to yield products. But the higher the barrier, the fewer the number of molecules with sufficient energy to get over. So how can we increase this number to get more product? Well, there are two things we can do. We can either increase the temperature so that more molecules have more energy and can pass over the barrier, or we can reduce the height of the barrier. And we can achieve that by adding a catalyst. So, for reactions which are thermodynamically possible, those for which G products is less than G reactants, but which don't go because the reactions are too slow to detect, we should be able to show that such reactions are indeed possible by increasing the rate of reaction. We can increase the rate by increasing the temperature or by adding a catalyst. So let's return to the ethanol decomposition reaction. If we try heating a sample of ethanol, then nothing happens for a long time, till about 500 degrees centigrade. But then the reaction that goes is not that giving carbon, water and methane, but this one, giving methane, hydrogen and carbon monoxide. So a reaction giving carbon is very reluctant to go. And indeed, no catalyst has yet been found to catalyze this decomposition at around room temperature. This tells us then that the activation energy for this particular reaction must be extremely high. Yet ethanol does undergo chemical reactions. Sodium reacts with ethanol to form sodium ethoxide with the evolution of hydrogen. This reaction, as well as being thermodynamically probable, occurs at an observable rate. Now, why should this reaction occur while the decomposition of ethanol, although thermodynamically favourable, does not? Let's compare the two reactions. The first reaction, the decomposition of ethanol, involves the breaking of many bonds: carbon-carbon, carbon-hydrogen, and carbon-oxygen bonds. Whereas the second involves the breaking of only oxygen-hydrogen bonds. This provides the explanation. Carbon-carbon and carbon-hydrogen bonds are difficult to break relative to oxygen-hydrogen bonds, and these will usually remain intact during a chemical reaction. So, for organic chemistry, thermodynamic data has to be used cautiously. If we were to predict the outcome of a reaction on thermodynamic principles alone, then invariably we would be wrong. In organic chemistry, what we need to look out for are not just thermodynamically favourable processes, but thermodynamically favourable processes which don't involve breaking carbon-carbon and carbon-hydrogen bonds. This emphasises the functional group approach. Reaction takes place not at the carbon-carbon or carbon-hydrogen bonds, but at the functional group. But just as ethanol is thermodynamically unstable, so are all the other chemicals in your home experiment kit. All of them have thermodynamically favourable decomposition routes, and so have all organic chemicals. And that means us. Just find the right catalyst and
René Descartes at the court of Queen Christina of Sweden. When Descartes went to Sweden in 1649, he was 53 years old and well established as a philosopher, scientist and mathematician. He was known throughout Europe and his writings were widely read. In the history of mathematics, Descartes has a principal role to play, as we'll see shortly. But standing behind Descartes in this purely imaginary group scene is a figure who, arguably, is central to the development of scientific and mathematical thinking in the early part of the 17th century. His name is Marin Mersenne. We start our story in Paris in the 1630s. Mersenne is a friar in the Mennonite convent of the Annunciation. The Mennonites, as the name implies, are a relatively small and humble order, but they have built for themselves a reputation for scientific investigation, with Mersenne amongst their most celebrated experimenters.
Amen.
Mersenne himself made a study of the nature of sound. His love of music made this a natural choice for his inquiring mind. But it was a subject not much studied at that time, and Mersenne was one of the first to do so. He discovered, by experiment, that the pitch of a plucked string is affected by several factors. First, it was proportional to the square root of the tension. Secondly, it was inversely proportional to the length. Thirdly, it was also inversely proportional to the square of the diameter. This formula was Mersenne's own discovery. It was completely new, and actually contrary to the accepted Pythagorean view of the relationship between tension and pitch. But Mersenne wasn't content with just an experimental determination of this relationship.
But why should this law hold? How can I prove mechanically that this law must hold true? I know that it is true to within the limited precision of my experimental observations. But can this formula be proved with the certitude of a mathematical explanation? The tension governs the movement of the string. But what is the nature of this movement? I have determined, using very long strings that vibrate very slowly, the manner in which the string behaves. But what are the physical laws that determine the manner of this vibration and related to the tension? And what are the harmonics of a plucked string? Without changing the length or the tension or any physical aspect, I can cause the string to behave differently. And produce notes of several different pitches. Now this I find puzzling enough, but I have listened deeply to many notes, and I have determined that plucking an open string can produce as many as 5 different tones at the same time.
This constant questioning of phenomena is characteristic of Mersenne's work. During his